All right, hey folks, hope you're all doing well. I wanted to take this opportunity to give another look back at the Bridge of Doom challenge, and specifically one aspect of it, which was examining the relationship between the left and right wheel velocities and the linear and angular velocity of the robot. Obviously, we moved on to other things in the course, but I thought some of you might appreciate this look back, and here we go. Okay, so let's draw out the scenario that we were dealing with in the Bridge of Doom. All right, so we had a coordinate system, a global coordinate system. All right, we'll call this I hat, J hat. Okay, and then we also had a Nito kind of floating off here. I'm going to draw it like this. Okay, and then we can think of the Nito as having its own coordinate system. I hat Nito, J hat Nito. All right, and then for completeness, we could also say that the K hat Nito axis was pointing out of the page and that the room's K hat axis was also pointing out of the page. Okay, so those two axes are going to turn out to always be the same because we're only moving in the I hat, J hat plane. All right, and then the position of the robot at any point in time is given by R of t. All right, and then we were interested in understanding how we can set the left and right wheel velocities in order to achieve some particular path of the robot itself. All right, so let me draw the left and right wheel. Okay, and we think of these left and right wheels as being along the J hat Nito axis. And let's further define the distance between those two wheels as script L. All right, we've also used the symbol D in order to denote this wheelbase, the distance between the two wheels. Here we're going to use script L because we're going to be doing some differentiation. So I want to avoid having overlap between the D symbol and the differential symbol. Okay, fantastic. All right, so we have this scenario here. Okay, so what we're going to do now is look back on where these particular formulas that we used in the challenge, where did they come from and how might we derive them on our own. All right, so the formulas we used in the challenge were VL, so the linear velocity of the left wheel is a linear velocity of the robot, or the speed of the robot along its heading direction, minus omega times d over 2. All right, and omega here, even though we've been thinking about omega often as a vector, here it was just a scalar, and what this represented as d theta dt, all right, where theta was defined as the angle between the axis, I hat axis of the room and the I hat n axis of the robot. Okay, and then positive theta was in the counterclockwise direction. All right, and then similarly, we had an equation for the right wheel velocity. Okay, so that was v plus omega d over 2. Okay, sorry, I realize I slipped back into using d instead of L. Let me just change that. Okay. All right, so now we're in terms of L. Okay, so this formula, we kind of looked at it qualitatively and made some sense of it. It seemed pretty reasonable. But let's suppose we had to derive it on our own. So there was a derivation linked from the assignment that showed how to think about that in terms of thinking about the point that the Nito is sort of rotating around instantaneously. But here we're going to use some of the calculus tools we built up in order to think about this problem. All right, so what we're going to do is focus on the left wheel. The derivation for the right wheel is going to be very similar. All right, so let's define another vector, okay, in space. We're going to call this RL of t, okay? So this is going to be the position of the left wheel of the robot as a function of time. All right, and what's beautiful about this is we can very easily write RL of t in terms of R of t and the j hat n axis as follows. All right, so to clean up the derivation from here on out, I'm going to leave time implicit in some of these vectors. So for instance, r is a vector function of t, but I'm just going to write vector r, and we're going to remember that that has a dependence on t. Okay, so RL is going to be equal to r, okay, plus L over 2 j hat nito. Okay, you should be able to see that the reason that is so is if we add the vector that points to the center of the robot here, and then add a little vector pointing along j hat n by the correct distance L over 2, we're going to get to RL. Similarly, we could define the same thing for R sub R for the right wheel, but that would be pretty similar, so we're going to leave that as an exercise for y'all to take up on your own. Okay, so now the fun part is when we take derivatives of both sides. So let's find the velocity of the left wheel. Okay, the velocity of the left wheel is the velocity of the center of the robot plus, and I'm going to put the constant out in front, the derivative of j hat n times L over 2. Okay, so this is where things get kind of interesting. So we're used to thinking about coordinate axes as fixed, right? So we think of the coordinate axes of the room as fixed, and of course they are. But in this case, the coordinate axes of the nito are actually changing. Remember, I hat n is always pointing tangent to the curve, and j hat n is always pointing perpendicular to the curve. And so if we want to take the derivative, we're going to have to do some work. Okay, and this goes back to a formula given on the Night 2 assignment that tells us how to differentiate a function in some other coordinate system with respect to the room's coordinate system. And so what it says is that the derivative, in this case we'll use the specific example of j hat n, with respect to the room is decomposed into two parts. It's the derivative of j hat n with respect to the body coordinate system or the nito coordinate system plus omega cross j hat n. Okay, and here omega is a proper angular velocity vector, right? Not just the scalar. Okay, and so, well, we know that with respect to the body coordinate system, j is fixed. It's not changing, so we can just zero that guy out. And then what we're left with is that the derivative is just going to be this part right here, omega cross j hat n. Okay, so I can go ahead and substitute that into my formula that I've been developing for the velocity of the left wheel as follows. Okay, omega cross j hat n. Okay, cool. So that's looking like we're making progress. Now the important thing to remember is what is omega as a vector? So remember, omega vector is decomposed into two things. One is a direction, which is the angle the axis that the body's rotating around, and the other one is going to be a magnitude, which is sort of the angular speed. So for a robot rotating the xy plane, omega is just going to be equal to d theta dt, so the angular rate of change of its heading times k hat nito, which points out of the page. All right, the I hat nito and j hat nito axes are 0. Okay, so substituting that in, we arrive at the following. K hat n cross j hat n. Okay, and here's where you'll see the really cool stuff happen. So if I use my hands, I point my index finger along the k hat nito axis and my middle finger along the j hat nito axis. I find that my thumb is pointing in the negative I hat nito axis. All right, so this whole thing is just negative I hat nito. Okay. And then we can just make this a minus. Okay, and now we have this beautiful expression for the left wheel velocity in terms of, whoops, I forgot the R here, the center of the robot's velocity minus L over 2 and the sort of angular speed. And this is I hat nito. Okay, so now we can start doing some cool things. We can start to say, all right, now what is the velocity or speed of the wheel oriented along the direction of the robot's heading? So what is the velocity along the I hat nito direction? All right, so in order to do that, all I have to do is dot each side of this equation with I hat n. So I can say that I hat n dot d by dt of RL is equal to I hat n dot d by dt of R minus, and I'm going to pull the scalars out in front just to make this a little more clear what's going on. Okay, and what you see here is that we've ended up with I hat dot I hat n, so that's going to be 1. And here we have I hat of n dot d by dt of R, okay? And if you remember, d by dt of R is just the tangent vector, which we know is always going to point in the I hat direction. So we could replace this with the magnitude of d by dt of R times I hat n, okay? Dot I hat n, which is going to be 1 again. Okay, so now we're left with the speed of the wheel in the direction of the Nito's heading is just going to be equal to the speed of the robot itself minus L over 2 times d theta dt. Okay, and if we look back on the formula we started with, we see that, wow, this is nothing other than VL, which is the forward speed of the wheel in the direction of the robot. This is none other than V, and this right here is none other than the scalar version of omega. So we've recovered the exact formula that we used in the challenge, this one right here. Okay, if we were interested, just for the sake of completeness, we could also take the dot product with the j hat Nito axis. So we might be interested in saying, is there any like lateral velocity of this wheel? We think probably no, because the wheel can't move in that direction, but we can just test it out by taking the appropriate dot product. Whoops, forgot an L here. Okay, so going back to our previous equation, j hat n dot magnitude, let's see, whoops, d by dt of R I hat Nito minus L over 2 d theta dt j hat Nito dot I hat Nito. Okay, and then what we see is that here we have a j hat Nito dot I hat Nito times the speed of the robot, okay, which is of course 0 because we have two perpendicular vectors. And then here we have d theta dt of this j hat Nito dot I hat Nito, which is of course also 0. Okay, so that shows us probably what we would have expected, which is that the velocity along the direction perpendicular to the Nito's heading is 0. Okay, so that's all well and good. Hopefully this makes a lot of sense. So you might say, well, what is this formula good for, or how might this approach be extended? So I invite you to consider a slightly different problem that will push things a little bit further. I'm not going to do it for you, but I think it would be a totally worthwhile one to check out, which is the shopping cart problem. All right, so let's imagine I have some shopping cart. Actually, let me draw it at an angle just to make it a little more general. Okay, so let's imagine we have our shopping cart here. Okay, and in the back, we have sort of fixed wheels. So we have like, well, that was bad timing. Okay, so we have a left wheel and a right wheel. And we can say, all right, we have a center point of our Nito, and we have a I hat shopping cart, and we can say we have j hat shopping cart. All right, and then we also have our global coordinate system, I hat j hat. Okay, and then we can say the position of the shopping cart is again going to be r of t. All right, and then the distance between these two wheels, as before, is L. And we could say that there's some additional wheels in the front. We can call these caster wheels. So these are ones that aren't fixed that have the ability to rotate. Okay, and we can call this CL and CR for caster left, caster right. Okay, and then we can define this distance as, I don't know, call it X. All All right. And so now I hope you can see that if I wanted to know the position of the left caster, it would be the position of the sort of center of the robot, or maybe it's a robotic shopping cart, plus L over 2 times J hat shopping cart plus X times I hat shopping cart. Okay, and so you could go through all the same math that we did before. You would get some, cross products. And what you would find is that the velocity of this left caster wheel is not always going to be completely parallel with the direction that the shopping cart's facing I hat S. There's going to be some component that points in the J hat S direction. Okay, and that should make intuitive sense if you've ever used a shopping cart. Okay, so hopefully this is a useful tool for y'all. So I'm going to go ahead and leave it there. If anybody wants to work this problem and has a solution to post, that'd be a pretty cool thing to share with the rest of the QEA community. So thanks, everybody. And let me know how this went for you. Okay, thanks a lot.